Welcome to Applied Materials and Corrosion. Unfortunately, my camera technology is very poor today, so we're going to have to make do with what we've got, which is just this board and my disembodied hand from the side. What I want to think about today is different surfaces and how they really look. So if we imagine that we've got this type of lattice and it's sodium chloride, for example, so we've got chloride ions as these blue ones, blue centers, and black centers being the sodium ions. If we imagine that we cut it in some way, because we've got to stop our crystal somewhere, we immediately run into a problem. So our normal materials science would be thinking of the sodium chloride as a bulk material or as a solution, but it doesn't think too much about what happens in between. That's what happens in our course now. So if we imagine we cut it on this plane, we would have plus minus, which was plus, this was plus minus. But if we imagine we cut it on this plane at a diagonal, then we end up with one face that's positive and one face that's negative that I'll now draw for you. So we can see that we've neatly cut our crystal between the positive ions and the negative ions, making one surface positive and the other surface negative, which is obviously a very weird thing to happen, but it could theoretically happen if we took a magic sword and we cut our crystal just randomly. So what would happen in reality now that we've done this? What happens, what do surfaces really look like after they've been cut? Well, they do something after they've been cut. They're not going to stay like this. They're going to capture some other material and change. So if we imagine going to a more simple case, which only has one type of atom, a completely covalent solid that only has two dimensions to make our life simpler so we can think about it first, then we can have this square lattice going into infinity in all directions, and that would be explainable from most purposes. And it would describe our solid material for most purposes, for material science, for the strength and conductivity and that kind of measurements that we might want to make, because those are measuring the bulk characteristics. It would also tell us the density and all kinds of things, and they would agree with what we would measure in reality. But the surface properties would not, because this doesn't have a surface yet. If we now cut our material here, using the toilet paper of slicing, then we have some bonds that are sticking out. In chemistry we would call these dangling bonds, but we've done something. We've got some kind of unsatisfied bonding that's now not doing what it normally would be doing in the bulk of the material, so something new has to happen. If we take the simplest case, so if this were something like carbon, for example, and we treat it specially, we could put hydrogen atoms on the ends of it, or fluorine atoms on the end of it. If it was glass, we could put OHs on the end of the silicon-oxygen bonds to terminate them, and then they would be happy. They would then have another atom that's a black atom, so they would then have another atom on the end. And they could theoretically, assuming these are small atoms, that's why I chose hydrogen and fluorine, because they're comparatively small, they would then not interfere very much with the rest of the lattice. But what we know from our material science, what you know from your material science, is that some metals have a more protective oxide layer than others. Aluminium is very, very reactive, titanium is very, very reactive, but they don't behave in a very reactive manner because they cover themselves with an oxide layer that's very protective and stops continued oxidation, continued reaction. But other metals, like, what's a good example of that? Other metals like iron don't have a very protective oxide layer, so once they start to rust, they continue rusting usually, although iron oxide is actually quite good. Iron hydroxide is very poor because it doesn't fit very well. So if we make this atom very big, then we can't fit one on here, is the equivalent of doing that. So if we take our whatever this is. So if we take our hydrogen off and we replace it with a much bigger molecule, say a sugar molecule, it can't possibly fit next to another sugar molecule only one atom away. And so therefore this next one will have to do something else. If we simplify that case, however, first, and we say let's just have nothing, let's imagine what happens if we do it in a vacuum. We take our magic surface, our crystal, and we cut it in some way, which we don't need to define right now. Then these atoms still won't just hang around like they are, because these bonds are very active. They're effectively single electrons that are stuck in orbitals, maybe 2 electrons. This one's got none, this one's got 2. Whatever's happened to those electrons, there used to be 2 in a bond, but now there's some unknown number between 0 and 2, and they are very reactive and wanting to do something. So they will rearrange to form a lower energy state. One possible lower energy state, the most common and the most simple one, would be if every other one reacts to form a double bond. So that would be this one over here, forms a double bond. This one has a single bond. So we end up with double single across our surface. This is what we really see. If we look at the crystal structure of silicon in a silicon wafer, we can measure the bulk crystal structure, and it has a certain distance between the atoms. And if we measure at the surface, we see more distance between the atoms, and they are actually bunching up into pairs and stitching together. So they've got an extra bond, they're closer together, and that uses up the extra bonding density and changes the surface, makes it less reactive than it would otherwise be. That's good, because otherwise our surface would just react with anything. But it's still quite reactive because obviously this is strained. This bond is unnaturally stretched because this double bond is smaller. It's stronger, so it will become smaller, and that will stretch this one. So this one is stretched and strained. This one is stretched and strained because it can't be as short as it would like to be. All of these bond angles are weird. Something is going on, and then it doesn't fit to the rest of our structure. What this means in reality is that the layers below our surface, several layers below our surface, are also distorted because the force on these atoms is incredibly high, and so it will distort the other atoms slightly lower. That means that we will have to dig quite deep. We'll have to use a measurement technique that looks quite deep inside our sample to be able to see what the bulk material would really look like. It's also very interesting if we have very, very tiny particles, because then we don't have very much before we come out the other side, and if we make them small enough, we won't have any other material that's in a bulk state at all. It will all be affected by the surface in some way. This doesn't happen just at empty interfaces, it also happens at interfaces between 2 different materials. So now I've put a black material on the top that has a completely different crystal structure, so it's got a 2-dimensional triangular structure, and the blue square material is below. Sorry about the weird background sound. That means that they don't agree, but I've arranged it in this case that they are some kind of multiple of each other, so the length of this bond fits exactly between 2 of these, and that allows the bonds to form properly, for it to be completely unstrained. But that is extremely unlikely to happen. Why should the bond length of this be some kind of multiple of the one below, and the number of bonds exactly match? So in this case I've allowed them to have 2 half bonds to each other, and that will allow it to be satisfied, although I have avoided the problem that the black ones would have broken 2 bonds and the blue ones would have only broken 1, so the number of electrons will also not add up. So we'll always end up with a problem unless we have extremely well matched materials. If we do this, we end up with a strain in this interface, and that will mean that the region between the 2 materials, both of them, will be distorted in some way. These bonds will not be the same length as in the normal material, these bonds will also not be the same length, they will be different. Okay, so if we take our rearranged surface with its double bond here, and carrying on into infinity in this direction and this direction, we can imagine the same thing happening as before, that some hydrogen comes along. Whoops, my pen is a bit shit. Some hydrogen coming along and reacting with the surface. So let's have that come along and react with this double bond here. The double bond switches out and makes a new surface. That will allow the surface to then, whoops, those should be black. Let's colour them in to make them look black. Let's make them black properly. And that will allow the rest of the surface, the rest of the material, these sub-layers to relax to their normal shape, which will take some of the strain out of these bonds here because they're all bent at the moment. So they will all go back to square. What that means is that the reaction here has much more development of energy. We get much more energy out than we would expect if we reacted hydrogen with a bulk material, because we're not reacting it with the bulk material, we're reacting it with the surface, and a lot of the energy that we're getting out is not we're breaking a bond and making a new one. We're actually breaking a completely strained bond and we're moving all the other bonds around to make it feel better. That gives us a new type of energy that we get out. We get out some rearrangement energy from our material. Now that sounds like it's esoteric and fairly unimportant. You would imagine it not to have a huge effect on anything, but let us think about a case where we're going to electrodeposit something onto the surface, so some black atoms that would then become something else, another metal. If we bring along an ion that will run out of pen, so it's going to have to be a blue atom instead, a shaded in blue atom. So if we bring along a new ion, that's a positive ion because it's going to be a metal, and we're putting electrons in here. Can we see that? Yeah. So we've got some electrons, we're pushing them through our metal into the solution. This is a solution, and we're going to deposit something new on the top. Then we discover that we see a lot of weirdness going along. So instead of having a layer that forms a completely normal interface and then we form bulk material above, we've got to do several steps. We've got to first of all add some lead or whatever it is, some new metal onto the surface, and maybe it goes in here and it takes this bond across. So it's going to, where's the other one going? The other one's going here. And maybe we don't fill all of these positions because these are bigger so they can't fit. And then we will eventually reach bulk material of this new layer on the top, this new metal. But then we have to get back to the state that we had before, where we had this still strained, but it's strained in a different way to match the new crystal structure of our other material. So we're now going to have a relatively complicated procedure. First of all, we're going to put on a layer that is not like the second metal. It is mostly fitting the structure of our first metal. Then the second metal will try to make its normal crystal structure, which will completely distort it, and then it will make its normal crystal structure right up here. So we're going to end up with a gradual development of different things. We can actually see this if we try to do an electrodeposition. So that will be getting on to one of our other topics later. But what I'm interested in right now is what happens when we put on a small amount. If we put on a small amount, we're not going to get a layer that's exactly the same as this, because they can't fit, they're too big. These ones are slightly bigger than these ones, so they're not going to fit on exactly 1-to-1 atom ratio, so they're not going to be able to go into this crystal structure. They're just too big. Their own crystal structure is different, and they don't yet have the power, they don't yet have the strength of structure or strength, the force to push these other blue atoms, sorry, they're all blue, but to push the original material into doing what they would like, which would be to have it a completely different crystal structure. And so to start with, they just go in between and sit in some positions where they're below the surface. So between, this one would be going into a hole between these two and behind, where there's another atom behind. Whether it's a square structure or a triangular structure, it would sit in between. The number of them that can fit depend on how they interact with each other, how many bonds that we have that we can use to attach to them, and what is going on. So if we think of it in a simplified case where we haven't got the distortion of rearrangement of the surface bonds joining to each other and bending everything, we can think of a surface layer that's completely flat, and we would like to add things to it. So we've added a partial layer. We've added these 1, 2, 3, 4, 5, 6, 7, 8 atoms onto the top, and we can think of that as an island on the surface. That's what they're called. So it's a layer on the surface, and we are trying to grow it in whatever way, either from a gas phase, so the new particles are coming in from here, they're atoms, so the new atoms are coming in from here, or we can think of it as an electrodeposition, so it's coming in solution. The lowest energy place that it can go is here on this corner, because here it can connect to both this one, it's making this inside corner feel better, it's making this outside corner feel better, because this one has very low number of neighbors compared to one in the center, which is connected to 8. This one is only connected to 3, so it's not got a partner here, it's not got a partner here, and it's got not one at the top. It's got a very low coordination compared to the ones in the middle. Sorry, these are connected to 6. This one's connected to 3. Then we can add one here and reduce the problem. It's a lot harder to start a new island over here, and so it will cost us more energy because we're only gaining 1 bond. If we put one on here, we gain 3 bonds. Once we've filled in this corner, we can only gain 2 bonds by adding the one after it, because it's now closed, and we can add the one that we add would come on here, and so it would be less advantageous to add a new one. This is exactly the same as surface tension, where surface tension comes from. So let's have a quick look at that and come back to this. So this is our liquid, and we can make our life easy by thinking of it as liquid argon. So all of these are argon atoms, and the only force between them is van der Waals interactions, and they are not directional. If we think of it as water, then we've got directional interactions, and we have multiple interactions. We have hydrogen bonding, we have dipole-dipole interactions. They're not the same length, they're not the same angle. We also have charge interactions. We also have these van der Waals interactions, and all of those are taking place in the water. It's rotating and it's doing things. Because argon has no directional interactions, whether it rotates or not is irrelevant. We can't even tell whether it's rotating or not, so it behaves as if it doesn't rotate. We don't have to worry about that. And the direction is irrelevant, so that simplifies our thought process here. So all of these argon atoms are attracting each other. This one in the middle is being attracted in all directions by its nearest neighbors, and attracted a little bit less by the second nearest neighbors, which are further away. Whoa, that gets out of focus over there. Yeah, sorry about that. If we look at this one on the surface, it is only attracted by half as many, effectively, because it's half of a sphere. It's only attracted by half as many, and so it has half as many positive interactions. This one is at a higher energy than this one down here. That makes it easier for this one to escape. It makes it easier for us to influence this one, and it also makes it more likely for new things to happen. So looking at our surface again, but from the top this time, So the same diagram as we had before, but we're now looking at the top. If we now start to add atoms to the surface, we first of all have to add one to this perfectly flat, perfect crystal, and that's going to be difficult. Then when we add another one, it's not quite as difficult because it can attach to a neighbor and form a bond. The third one is difficult again. But the fourth one forms the fourth corner, so that one is comparatively easy because it forms more bonds. As we increase the surface, effectively most of the time we are adding a new atom. Let's make it a little bit bigger to start with so it's easier to imagine. Let's make it this big. So we're now going to add a new row. Let's add the row on this side because it's closer to me. So first of all we're going to add an atom somewhere, and then as we go along we're filling the row in. Filling the row in is better because we're effectively making 2 bonds every time. So as we go along we make 2 bonds every time, every step. 2 bonds, 2 in plane, plus the 1 going down. Once we've completely filled the layer, we've got the same problem again, that there is nothing to bond it to, and so we discover that it is then harder again to add the next atom. If we do this in a vacuum and measure it very carefully, we can measure differences in the energy as we go through layers. So we add a first layer that is initially difficult, and then it becomes easy, and then we have a difficult bit again as we start a new layer because it has completely filled. If we have a lot of energy in our system, it will start a lot of islands all over. If we just add enough energy so that it can start one island, then it will grow completely. And then it will stop again because it doesn't have enough energy to make a new one. So we can, if we can control the energy in the system, which is temperature in many cases, or voltage if we're doing electrodeposition, if we can control the energy very carefully, we can stop it at a reasonably finished level. However, there is a problem. So the problem that I'm going to stop on, or the issue that I'm going to stop on, is defects. The defects you will know from your metallic materials courses. These crystal structures aren't really perfect. There are atoms out of place, there are bonds that aren't to the correct place, and so interesting things happen. So in this case we've got a defect where this atom here doesn't have a friend below it. It would have one in the other dimension, but it wouldn't have one below it, and that will make this site higher in energy. It's got effectively, this atom has extra bonding electrons that it can use to attach to things, and so that enables the next layer to form more easily. Or if we're dissolving it, as you know, this atom is obviously a target because it's not as well held in as the others. And these can then rearrange to form a more perfect crystal, but usually they are also starting to be removed at that point. The most interesting type of defect that we can have in this is a spiral defect, which I can't draw very easily. It's a defect where the atoms, the layers, are not connected to the right place in a spiral. It's a line defect in, technically it's a line defect in out of the plane, perpendicular to the plane, but what we actually see is a line in plane. So let us see whether I can show you an example. So my most effective way to explain this, it's an easy one to explain badly, so I'll try hard, but maybe I'll fail. My best way to explain this is if we take a stack of paper, that would be the layers of the crystal in this direction, and we tear it to the center of our defect, like that. Oops, let me show you, like that. So I put a tear in it, it's old exams, and then I bend these so that they're shifted, one is shifted up one, the next one is shifted down one, and then we bond them all back together. If we take that type of defect and we follow around, we would go round here, and then we would go to the next page effectively, because this edge is now pushed down one and connected to the next sheet down, and we follow it round and we get to the next one, and we get to the next one. The important thing about this defect is that it is a both directional low energy defect that avoids exactly the problem that we just covered. So the problem that we just covered is it's difficult to start an island. It costs more energy to start the next layer. But here, the layer will never be filled because we fill from the edge of our spiral. There's my spiral. So we fill from the edge of our spiral, and it goes round, and when it comes back, it still doesn't fit, very much like a roll of sellotape. As we pull it round, we get to the next layer, and we carry on spiraling round and round. There is no line. There's a line defect, but the line sweeps round and round, and it looks the same at any angle, so there is no tear, or better said, the tear is constant. It stays there whatever we do. This is good for growing things because we have a continuous growth on the edge of this growing edge. It's a continuous line edge, and our new atoms can stick here, or molecules, whatever they are, can stick on here and go round and round and round and grow another layer, and then they can continue, and it never fills up, and so it never blocks. We don't get this steppy energy process. On the negative side, we can call it the negative side, if we like our material to stay stable, when we start to dissolve it, when we start to etch it, it can attack, our etchant can attack at the edge of the step edge, and it will unpeel, but it never stops. Unlike when we had just a normal defect where we take one atom out, one row out, and it's completely stable again. We get back to a normal atom, a normal crystal, sorry. In this case, our crystal structure stays constant all the way through, and we effectively drill right the way through our crystal. We can remove the whole crystal if it's got a spiral defect in it. The problem being that they also grow very fast. So it works in both directions, but obviously that's going to mean that if we have a spiral defect to start with, that will grow preferentially to the rest of our material. And that means that when we try to etch it, it will etch preferentially to the rest of our material as well. And so that can be a bad thing, and it can be very difficult to avoid, because obviously when we're trying to grow our crystals, the ones with spiral defects will tend to grow faster than other ones, because that is a particular way where we can smooth out the energy, and if we're growing it very slowly, that one will just carry on growing, and all of the other ones will stop every time they put a complete layer across. So I will stop for today. I'm still waiting for a better camera. Sorry about the fuzziness. It's potato vision. This is the worst camera that I've got, but because I need the other one for a different thing. I'm getting a new camera. It should be better. That's the reason why I'm not making too many videos at the moment, because I'm hoping I can have better quality, higher resolution, and not so flickery. We will come back to this next time.